Hello, everyone. Thanks for joining today. It's great to introduce Katherine Driggs-Campbell, who is an assistant professor at the University of Illinois at Urbana-Champaign in the Department of Electrical and Computer Engineering. Katherine directs the Human-Centered Autonomy Lab, where she develops robotic systems that operate in the world around people. And prior to that, postdoc researcher at Stanford and PhD and master's at Berkeley. And I just learned that she also spent a bit of time at MIT. Katherine's research focuses on methods for modeling and predicting human behavior, on frameworks for robust decision and control, and safety verification in multi-agent systems. And today, Katherine will talk about safety and failures in autonomous robotic systems, being mindful of the system structure is important to be able to address domains as ranging from autonomous driving, agriculture, and crowd navigation. Thank you, Katherine, for making the trip all the way to MIT, and thanks for coming in person. Welcome. The stage is yours.
Awesome. Well, thank you for that very kind introduction. And so I see we're very compact over here. So if at any point you have any questions or need any clarifications, go ahead and raise your hand, and we can have a bit of a conversation. So I'm not just talking at you guys. All right. Well, again, thanks for having me. I'm super excited to be here, and I'm super excited to talk about some of our recent work. And this work is in collaboration with Roy Dong, Peter Du, and Tianchen Ji, who did most of the heavy lifting. But so today we're going to talk about our failures. So instead of talking about all the really cool things we can do, we're going to actually talk about all the things that we really can't do. And the idea is if we start really thinking about the cases and scenarios in which our systems fail, we should have a better idea of when we can trust them. Hopefully this will actually bring us closer to this point where we can really deploy them in practice. So as a bit of motivation, broadly speaking, we already sort of got, I guess, some introduction to what my group does, but broadly speaking, my group tries to answer this question. So how do we design these safe, autonomous or robotic systems that operate with people out in the real world? So the two sort of operative words here are safe and with people. So we look a lot at how we can model human behavior. We use a lot of tools from learning and optimization and decision making and control to sort of make sure that all the modeling that we do of these human behaviors can be realized on our robotic system. And we have these sort of safety guarantees, hopefully. We try and do as much as we can, as much deployment on real systems, so sort of the proof of the proof, to make sure that we are getting things as sort of realistic as possible, and we're really capturing some of these sort of real-world uncertainties when we're developing our systems. And the end goal is hopefully, as we really start pushing towards deployment, we can now get to the point where when it's out in the wild, when it's operating with people, not in lab settings, we're still getting some of the nice guarantees or the nice properties that we see sort of in lab and in practice. And I think this last point, sort of pushing to deployment, is becoming very important for the robotics community, as I think there's a lot of systems that are really close to that point where they're about to enter sort of everyday's lives and really transform sort of how we operate and how things go. So this is sort of a transportation-motivated slide, but in general, my group looks at a bunch of different domains. So in transportation, we look at how to design these autonomous systems that take into account these human considerations. So be that humans around our autonomous vehicle or the driver within. We look at manufacturing contexts, where we're really looking at cases where we're looking at safe collaborative systems. So again, pushing that sort of modeling human behavior so we can have these sort of safe interactions. We also look at agriculture, which is sort of embracing that Illinois culture, where we're looking at these mobile robots that can go up and down our fields and help assist farmers in practice. And more recently, we've been playing with home robotics. The video seems to have stopped, but where we're really looking at sort of crowd navigation and how we can use these mobile systems that interact and can help us around in our homes. So to draw sort of some insight from these specific domains, we'll take a sort of subset of these and try and see if we can find some insights across these different domains. So one of the things I would like to highlight here is at least the way I've ordered them. We sort of see this notion of increasing structure. Okay? So if we look at the manufacturing context or setting, this is a scenario where we have really well-modeled robots typically. We can sort of build in a lot of infrastructure to make sure some assumptions that we want to make are met, and we have a lot of control over our environment typically. If we move down to transportation, we still actually have a lot of structure in our problem where we have rules of the road, there's sort of expected behaviors, but we do see this sort of like degradation in the structure inherent in the task when we start looking at the interactions that happen or we see some sort of violations or sort of variance in the environment. So if we start sort of really expanding to things that we can't control like weather or crazy human behaviors. So we start seeing this sort of breakdown of structure. And then on this far end, we have sort of this field robot case where really we have a ton of uncertainty and it becomes very hard to sort of model and understand what's going on here. So in particular, in this case, not only do we have just all the sort of uncertainties of how the robot's going to move through things like mud, but the environment itself is constantly changing. So we have lots of wind, so even if you aren't moving your robot, it can appear like you're moving just because of the way the sort of plants move around you. And coming up with sort of good models of this is very, very challenging. So this is very important when we start thinking about safety, because basically how we start assessing these systems varies a lot based on what we can actually analyze and how we can sort of take advantage of models. So for example, in transportation, we might be able to start doing some simulations. We can get some insights. We can find these failures. We have a sort of good idea of what we're looking for. But basically what we need to do is sort of come up with these agent models and have some sort of foundation there. So in contrast, for manufacturing, we often have a very sort of precise process. So this is sort of a low-level example of we have some thing that we're trying to create. We are sort of producing or providing that process. So coming up with sort of concrete characterizations of failures becomes very clear, again, because we have a lot of control in sort of what we're trying to do. And again, on this sort of far end, in agriculture, we sort of have these situations where it becomes very hard to even sort of specify what a failure is. So defining sort of all the criterion for what is a collision becomes very hard, and it's just very sort of hard to capture all these uncertainties. Okay, so on some level, we can sort of analyze safety and sort of how we specify our failures based on this structure. And so before we sort of jump back to that, which will be sort of the core focus of the talk, one other sort of observation I would like to note is if we sort of expand this view of structure a little bit, we can add a y-axis here and look at this sort of, I guess, vague notion of sort of level of autonomy or the different types of interactions that arise. And this does change as you look at these sort of different structures or things that are inherent in the task itself. So when I say level of autonomy, I think everyone knows what this means for transportation. On sort of the top here, we have very high levels of autonomy, or level 5, where we have the fully autonomous agent. And if we decrease the level of autonomy, we get down to this sort of level 1, where we're really looking at the assistive systems where we interact with the driver. In the manufacturing setting, you can kind of see some similar things where current practice is really looking at how we can sort of automate the whole process. We have these robots that are working in isolation. They are highly, highly automated. And a lot of what at least we're working on is sort of almost sort of increasing the intelligence, but in many ways decreasing the amount of automation and really looking at how we can couple these systems and make them more flexible and make them more adaptive. And in the ag case, we have the low levels of autonomy where we sort of have this one-to-one matching, where we have the robot that's really augmenting what a human is doing. It's almost sort of an extension of what the human can do. But if we move to higher levels of autonomy, we start really thinking about the supervisory control. So a few things to sort of note is sort of how to relate this more to structure. If we sort of look at different slices of these sort of, again, sort of vague notions of modes of interaction or levels of autonomy, we can kind of see that there's some differences in what we need. So if we sort of move down this direction here, we have more like shared control or sort of really tight physical interactions. And that sort of decreases as you go to less structure. And on the top here, we have different roles and sort of presences of the human. So on the sort of far end, there's basically no human there, or limited human. Whereas on this end, the chance of sort of eliminating the human completely is very, very low. Okay, so that's sort of the quick pitch, sort of motivating this idea of thinking about structure. But again, so today we're going to be talking about sort of building on this idea that depending on what we can say about our domain or about our task really determines how we assess the failures or how we assess basically the safety of the system. Okay, so we're going to look at little snapshots, sort of taking different pieces in the amount of structure we can assume, or basically how we model some of the uncertainties in the system. So we're going to go in kind of a wonky order here. So we're going to start sort of in the middle. So we're going to start with simulation-based validation, and this is very motivated by some of the challenges that you'll see in the transportation world, specifically with autonomous vehicles. We'll move to sort of a more classical approach, where if we have a really good model, we can kind of deep dive and start understanding and characterizing the failures that we'll see. And then finally, we'll move to a very unstructured case where we really have a hard time coming up with a concrete model of our system, and we'll really look at sort of anomalous behaviors. Okay, so let's jump in. So okay, we're going to start with this simulation-based validation. So even though we're going to be talking a lot about simulation later, a lot of this is motivated by some real-world tests that we conducted in collaboration with SVAE and some folks at Stanford. So in this project, we were trying to come up with ways to come up with safe and efficient urban driving. So you can kind of imagine the things that we were working on. So I've showed this video a few times now, but we were looking at these sort of urban driving scenarios, and also, I guess it's expanded to some of the other usual subjects, learning from human drivers, and we were playing a bit with different representations of perception. But we're not here to talk about this. We're here to talk about our failures. So let's talk about some of the intervention scenarios that we had. So these are some just example sort of key points that when we were doing some tests, we found some failures. So in this case, this is when we were testing a lane changing controller. So here we're following this car. There's another agent, which you can kind of see, I think, in the lighter point cloud here. We're going to start executing a lane change. And at some point, we just start sort of veering back to the car, and then we release control. So we just sort of start going back. So this is a bad case. This is not what we want. So this was one of our intervention scenarios. And when we started sort of digging through this, what we think the problem was model mismatch. So there was some gap basically in what the limits of the actual car were and what we were actually running the optimization on in simulation. So it basically thought that it would be able to complete this execution, but it was not actually able to. And I put a question mark here because this is our best guess, but it's hard to sort of know after the fact. So, okay, so this is one example. Here's another one. So we come up to this intersection, and you can see in this little sort of camera screenshot here, we have a lot of glare from the sun here. It's a little bit hard to see. Let me see if I can actually, can you see my mouse? You cannot see my mouse. You can sort of see, I think, maybe you can't. There's some bounding boxes with cars, but they're actually flickering in and out. So in this scenario, the car basically comes up to the intersection and is just waiting. So it basically is getting sort of mixed signals about whether or not it can go. And this basically came down to some uncertainty in the perception representation. So these are some failures that we encountered. Now, for all of you who have, I guess, had some experience making your videos for ICRA or whatever, seeing these sorts of videos is probably not that surprising. This is something that you probably all encounter. And what you do is you sort of see these problems, and then you fix them, and then you try again. So a lot of what we'll try and do is try and see if there's a more sort of formal or rigorous way that we can start finding these failures to sort of improve and facilitate the process without basically this sort of last-minute hacking and whatnot. Okay, so another sort of nice thing about these sorts of failures is actually these two failures can actually be captured or fixed by a lot of robust control techniques. Because a lot of this comes down to model mismatch, which is basically saying that we need a better model of our uncertainty or some unmodeled phenomenon. So if we were to take sort of a classic decision-making or robust control approach, or a robust decision and control approach, we can sort of formalize this as follows. So if we have some system that we want to control, in this case, a vehicle, we have our normal dynamics model here. So this is f, this is a function of u, this is our controller that we basically use to try to get the system to do what we want. And then we often add some disturbance. And this disturbance is meant to capture this unmodeled phenomenon or be sort of this noise term here. So basically, for this, if we have some of this model mismatch, we have some uncertainty, often we can kind of bake it in here. And this is not anything particularly new. This is very common and sort of came about by handling this sort of sensor noise or environment uncertainty. So we can kind of capture these sort of in the process as we're designing our control, and we can basically find things that are robust to these sorts of disturbances. This sort of modeling framework has also gained a lot of attention recently as there's sort of a rise in learning-based control to help compensate for things like model mismatch. So you have some simulator that you're training your system on, but there's the real system that you want to deploy it. This model mismatch can also be basically modeled or captured by this sort of very right-hand term here. Okay. So this sort of formulation, again, has a very solid foundation. There's lots of work in this area, but it actually it doesn't capture general failures when we start really thinking about the deployment case. So when we really start thinking about sort of more longer term or sequential interactions that could lead to failures, this approach doesn't typically work very well. So one of the things we wanted to do is start seeing if we can sort of push how we understand failures and push how we design the robustness of our systems to really capture some of these more longer term and interactive failures here. So this is motivated, or this in some level doesn't seem like it should be that challenging, but in the autonomous vehicle scenario, and actually in many systems where you are sort of ready for deployment, you have this issue where often your sort of high-risk events are also low probability. So if we look at the sort of collision rates or fatality rates for human drivers, we can see there's actually a big, very, very large gap between these events. So these are very, very low probability. So if you really wanted to start showing that your system was as good as a human driver, you'd have to drive for orders of magnitude more than this number here, so like 1 billion kilometers driven to just sort of get a good understanding of whether or not you're actually beating human drivers. And another thing to note here is if you wanted to do this on your real car, you also have to sort of recognize that not all miles are equal. If you're just driving on highways, it's actually fairly easy driving. If you really want to show how good you are, you should circle parking lots. It's actually one of the highest collision places. But anyways, so often getting these miles driven on the real system is very hard. So getting sort of this statistically significant sample is very hard, it's very expensive, and it's not very easy for people like us in academia to do. So to help resolve this, a lot of people turn to simulation to sort of help augment or sort of give a little bit more information for this. So if we had some simulation, so let's look at this sample scenario where we have a vehicle that is approaching a crosswalk and we have a pedestrian that's there. So if you were designing this simulation, you might say, okay, I want to check if my system is safe for all realizations of what the human could do. That is non-trivial. So often what you'll do is you sort of discretize some speed or come up with some simplified model and you propagate this forward. Maybe this isn't expressive enough, or depending on your model, you might expand this a bit. So maybe you will also consider some lateral motions, some other sorts of behaviors. But the problem is usually when we're designing these models, they often sort of work in expectation, or we're sort of designing them to do what we expect. So they might not capture some sort of weird behaviors. And while on some level, maybe this seems too weird, maybe this isn't something you want, but it's sort of hard to know in advance, and you want to really make sure that your system is going to be safe even in these sort of weird realizations here. Okay, so say you're designing your simulation, you could encode or come up with a model for all of these different situations. So that's all well and fine. But then if you are looking at sort of a more general situation, you might add some more agents, which also has some variable behaviors. You're quickly getting to this situation where things are very complex. So you have lots of agents that can do lots of different things, and it becomes actually very or almost just as challenging to get meaningful simulations or find these sort of meaningful situations even in simulations. So just computing all of these different factors still becomes sort of a challenge. So one of the things that we want to do is design a tool or think of approaches so we can basically resolve some of these situations. So we want to efficiently find something, say, like trajectories that result in failure to help sort of give us some idea of what's going on in an efficient way. So we don't have to do complete coverage of our model, but just try and likely failures here. So to do this, we developed a tool called adaptive stress testing, which we call AST. And basically what this tool does is it takes advantage of recent advancements in RL solvers to basically efficiently query or search your simulation space to find failures here. So in your simulation, you can encode your whole world. You have some model of the different agents. It's good if you have some places where you know your sort of uncertainty can come in, or where you can sort of insert some of these noises. And your solver here is basically trying to control this noise or some environment actions here, and it's trying to optimize this reward that will guide it to failure. And the environment actions, so we'll talk about this a little bit more later, but they can be very precise. So you can think about actions of the different agents. So you can look at specifically adversarial agents. Or this also works pretty well with just random seeds. So instead of controlling specific agents, you just sort of control your uncertainty, and you just find sort of situations in your environment that do lead to failure. So the key thing here, though, is we need a good reward. So we need a good reward that can basically guide the simulation and help us sort of push it to these situations. So AST basically rephrases, again, this validation problem or task as a sequential decision-making problem. And we define this word as follows. So basically, we're trying to find some failure here. So here we give it basically no penalty here. We have a large penalty if we find no failure here. And we also have a penalty for choosing basically very unlikely actions. So basically, by just looking at this, this reward, basically what this is guiding the search to do is find these failures that are very likely to happen here. And there's a few sort of different pieces here that are kind of grayed out, so they're hard to see. I don't know how it's hard for me to see from this angle. Hopefully it's easier for you guys out there. But this is basically some heuristics to help guide your simulation. So on some level, you kind of just want to let the system search and sort of put minimal guidance. But if there's some things that you know will help you find your failure, you can add these heuristics in to help basically guide and sort of narrow the search here. So for example, if in the autonomous driving case, you know you're looking for collisions, so you can basically guide the simulation to find situations where you're sort of minimizing that gap. Or you can use some other sort of domain knowledge that you can add in there. And while at some level this is kind of a simple solution to the problem, something that's really nice about sort of looking at the validation with this reward structure is it doesn't make it very easy for non-experts or experts in just sort of the in other areas to use. So this sort of simple solution makes it very easy when you're working with collaborators, and it has been adopted by a number of people in industry. And it's sort of nice that people can just sort of tune these heuristics and sort of easily see how the search happens. Okay, so let's do a quick example here. So we're going to look at a multi-agent crosswalk case. So this is similar to what we had before. So we have our agent and our pedestrian here. In this case, we have sort of a fine model of our simulation. So we have these participant dynamics. So these participant dynamics can be this pedestrian, for example. And we have some noise that we want to look at as well. So when we're thinking about the environment actions that we can control, we're going to control both our agent as well as these noisy actions here. So AST, the solver, is basically going to actively search this space, control both this agent and the noise in the system to help us find some new failures here. Depending on your choice of solver, you might get some sort of different behaviors out. You can try a bunch of different solvers. We most commonly use MCTS. So it gives us, so this is Monte Carlo tree search, gives us a bit more structure than some of the more learning-based methods, or more deep learning-based methods, I should say. And the other sort of nice thing about Monte Carlo tree search is we are able to sort of look at risk evolution through time as we're sort of building up this tree. So we're able to sort of track this likelihood of different actions. And it kind of has this nice correlation to risk. And this is very similar to work in the statistical model checking community, where they use similar tools in Monte Carlo simulation. OK, so we have this example. We're able to sort of probe the system. Let's sort of look at things that might come out. So if we were to have this typical simulation, again, because we sort of tend to sort of produce simulations that do expected behavior, if you run your simulation a bunch of times, you'd get some sort of situation like this, where sort of everything looks good, everything is nice. OK, so now this is case one. Now the other case two is if we do sort of a pure adversarial simulation, we actually also get failures that maybe we don't really want. So this is the video I showed before, where we just have this pedestrian that just runs straight to the autonomous vehicle, which, yes, is a failure, but that's not really insightful when we're thinking about the design process, because this isn't really something that we can stop. This isn't a case where we're at fault. So in these sorts of situations, we not only, I guess, one, could encode something like we only are interested in situations where we are at fault, sort of reduce our failure search a little bit, or we can think a little bit more about how to sort of model that likelihood of actions. So if we really look at these relevant failures, we can find situations like this. So this is a case where it's mostly a cause or an issue with our noise in our perception system, which is something that we care about a little bit more here. So we can see that it's, again, maybe it's hard to see, but this bounding box is sort of moving a lot around the pedestrian. So this can help us give us an idea of basically where the limits of our system are. And again, this can help basically this feedback loop and how we're basically updating and fixing our system here. OK, so this is mostly it for adaptive stress testing. I think there's a few sort of general challenges with it, though. So in particular, one of the problems with using this sort of RL solver approach to search the space is typically when you're trying to find a policy through RL, you're trying to find one policy that is optimal. So in this case, maybe we do want to find one failure that is the most likely, so we can address it first. But really what we want is sort of a diverse set of failures, so we can start addressing all of them and, again, have a better idea of the different situations in which our system fails. However, this is sort of not that easy to do given the sort of current methods. So you can do a few different things like restart and sort of reshape your policy based on your past observations, but there's some sort of tricks to do that as well. And I guess one other thing to point out is the situations, the simulations here are relatively simple, but you can scale this up to full traffic simulations. And like I said, it's something that is now put in place in practice with a few industry collaborators. So a few other things to note. So this is sort of an example of AST sort of working here, but there's also some sort of nice connections to the sort of more interaction step here. So a lot of the search methods that we talked about are based on basically heuristics that can help guide it, and it really is sort of biased by preconceptions of what a sort of what safety is or what we sort of want in our failures. But one thing that you can do is you can extend this and sort of get some feedback from people about what a dangerous situation is and have basically some perceived safety metrics in the loop as well. So you can get more diverse types of failures. So you can get things that aren't necessarily strict collisions or sort of risky events, but you can get things like cutting off behavior, which is also bad, but maybe not directly dangerous. Another thing that we've been playing around with is actually using this to compare policies. So if you have, say, two policies in crowd navigation, they might have similar metrics, but it's actually hard to sort of actually compare which one is better than another in a more sort of qualitative sense. So one of the things that we've been working on is adapting AST to actually find divergences in policies. So you can say whether, or in situations where one policy is better than another. We're hoping that this will actually help us with some interactive policies, since one of the things that we found is when we have policies that do a lot of prediction and sort of understanding of human behavior, there's only some situations where they really make a difference. So we're hoping that this will sort of help us find those. OK. So that's basically all we have for this validation approach. And again, sort of in this approach, we're sort of assuming that we have some sort of understanding of these agent behaviors and some sort of simulation that we can run. So we have some other situations if we have a more sort of structured model, and we can kind of better capture the nuances and come up with a more sort of guaranteed approach of where and when our failures are going to happen. So again, in this sort of situation, we get sort of more empirical results. One of the things we might want is to actually get sort of a more rigorous understanding of safety, which kind of feels better when you're actually talking about safety here. Okay, so to do this, we're going to kind of jump into some math. So it's going to get a little tutorial-y feeling for a bit, but then we'll end at the ends, and I'll try to not go over too far with just some sort of fun videos of failures in the end here. But okay. So let's sort of jump into this more rigorous analysis. Okay, so typically when you talk about safety in the more strict sense, you often see sort of pictures that look like this. So typically you have some safety criteria that you'd like to meet, and you basically want to find configurations or initial states of your system that sort of satisfy this. So this is approached by both the control community as well as the formal methods community, and it's basically trying to look at basically realizations and check if some property holds for your system. So often in the probabilistic sense, we also want to look at some probability. So you maybe don't want to just see situations if some property always holds, but you might want to see up to some probability. So it's okay if you violate your safety constraints, you go into this unsafe set, as long as it's sort of below some threshold. And having some probability threshold is sort of a nice analog to sort of this strict, is it safe or not guarantee, because it directly ties to risk, where you have some sort of cost of a failure times the probability gives your overall sort of sense of risk. So typically in the sort of control approach, you often are looking at this from a reachability perspective, where you're basically trying to, again, find these initial states or see if a controller exists that satisfy this state up to some sort of probability. You can also look at P safety, which again is basically putting this P threshold, and you want to say, given some system, does it satisfy this here? And sort of this sort of view, and as I sort of mentioned, this sort of picture is sort of the predominant view and sort of the most common approach for safety. But one of the things that we've been thinking about is coming up with a slightly different approach. And this is looking explicitly at exit times. So now we want to see basically, instead of just saying, looking at this sort of Boolean property, we want to look a little bit more at analyzing when and where we'll actually exit our safe set. So we're going to do this in terms of exit times. So as a sort of simple example here, let's say we have two policies for some robot. We have some case where it fails with very high probability, about in the middle of the field. And we have another situation where it may fail either at the beginning or the end. So these sort of two policies will satisfy the same safety properties, or could satisfy similar safety properties. But one policy is actually drastically better or preferred over the other. So we actually much prefer this orange one, so we can either rescue it at the end or it almost completes its task. So extending things to sort of look more carefully at when the system fails gives a lot more insight about the sort of underlying behaviors of the policy itself. And so this idea of looking at exit times is not necessarily a new idea. It's an approach that's sort of gone on or been sort of pursued by the stochastic hybrid systems community, but really it's sort of been limited to very theoretical settings. So some of the things that we're going to be talking about now are basically going through that formulation and talking about some of the computational considerations if we actually wanted to start thinking about this for robots. Okay. So first, a lot of this work is based off stochastic differential equations, or SDEs. So again, we're assuming that we have a lot of structure in our model, and we have basically a good way to capture this sort of diffusion or this sort of uncertainty term. So that's sort of the crux of what we need in this sort of formulation. So we have this drift component, which is our sort of deterministic model. This is very relatively easy to capture. Often the hard part is capturing the noise and some of this uncertainty, as we sort of highlighted in these other cases. Okay, so we're assuming we sort of have this SDE model. Now, there are a few sort of nice properties. So in some ways, SDEs are just sort of a nice extension of ODEs, but they have a few nice properties that we can start using for analysis. So first, we can define this generator function, which I'm going to try and go a little bit quickly. I apologize, but we're running a little low on time. But basically what this infinitesimal generator does is it gives us basically this expected derivative, or this derivative in terms of expectation, which basically gives us this sort of one-step, very small prediction of our system. And we can sort of define this for all test functions, but this is basically something that we can correspond with this SDE here. If we plug this into our SDE, we're actually produce a martingale. So this means this expectation holds. So what's nice about this expectation here is this gives us basically a linear constraint. So we can start analyzing our system by looking at basically this constraint here. Okay. One other sort of nice thing is if we are looking at Ito processes, we have this nice lemma that gives us basically this nice linear functional for this stochastic differential equation here. So basically, we can clearly define everything that we need for this function here, or for this equality here. Okay, so this is basically just some nice properties, SDEs, that we can start using to start analyzing, again, these exit times. So when we say exit times, basically we want to find this minimum time that we first leave our set. So this is basically this time of first failure. Now this value tau is actually a random variable here. So it's actually sort of a random process in and of itself. So it's a little bit hard to analyze. But there's some nice work that basically says our expectation from the previous slide still holds as long as this is a bounded number here. So often what we do is we basically want to check if there's an exit time before some finite time horizon that we pick. So now we have this sort of finite time that we're analyzing, so we still have this equation that's true. Okay, so this is basically how we define our exit times. Now let's sort of think about how we might actually evaluate these expectations. So there's two quick things that we want to look at. So first we'll look at occupation measures. So we define two different measures here. So first we want to basically have some measure that can basically tell us how much time we're spending in a particular set. So this first function here is basically telling us how long we're in some set B. We'll replace this with our safe set when we want to basically see how long we're living in our safe set up to our exit time. The other measure that we'll introduce is basically this point or exit location. So we basically want to look at that probability of that exit, basically of when we exit along the boundary of some set. Okay, so now if we sort of combine these two equations together, now we have this sort of nice equation here where we're now evaluating this first expectation with respect to our exit time measure here and our occupation measure here. So there's sort of two key things to note is first, this measure is basically supported by our safe set, and this here has the support of our boundary here. So basically, coming up with good representations of our safe set and its boundary actually will become a sort of important point. Okay, so we have this equation. We're almost through it. We're almost through the weeds. So one of the sort of nice things here is so we have this explicit function for our generator. And if we look at a certain class of functions f, specifically monomials, we also get some very nice properties. So if we plug in monomials, this means our generator is going to be polynomials, which gives us a really nice sort of characterization of these exit times in terms of the moments. So because if we're looking at the integration of a polynomial and we break this up, this actually just becomes a linear combination of our moments of our function. So this doesn't give us the exact distribution, but it does give us some good characterization of basically when we're leaving our set here. So I'll skip through a little bit of this stuff here, but basically what this means is we can now take this sort of nitty-gritty integral here, and we can convert this to some linear constraints here, where we're basically looking at this linear combination of our moments of our functions here. Okay, so two things to note. If we looked at this in sort of the infinite case, we can have an exact solution or description for our exit time. I cannot compute things infinitely, so often we'll say we'll compute the moments up to some finite number, so we'll sort of set the number of constraints that or moments that we look at. But basically what this does is this reduces the constraints of the problem. So we no longer have a unique solution. So we need to look at sets of solutions here. So we can throw this into an optimization where we can basically find these optimizations here. So I'll sort of skip through this in the interest of time, but you can formulate this as an optimization here. And basically what you'll get is a lot of positive semi-definite constraints here, because you need to basically capture that these moments are valid moments and sort of abide by these nice properties here. So this is existing work here. And the nice thing about it is it's a convex problem. Some things are very nice. But there's a sort of a number of issues here. In particular, this last bit, which I didn't necessarily explain, but this is basically saying you're supported on your safe set and your boundary. And coming up with good representations of these values is really not trivial here. So a lot of what we've been doing is basically trying to see if we can take some of these really complex constraints and turn them into equality constraints and help sort of define where these safe sets are here. So again, some of these PSD constraints or positive semi-definite constraints scale very poorly as you sort of have a more complicated optimization. And again, a lot of this is sort of dependent on that safe set. And these are actually very hard to capture. So as a simple example, so in the past, a lot of the work on this is sort of demonstrated on like 1D systems. So if you have a typical safe set, you might have something like the norm of x is less than or equal to 1. Okay, so the boundary is very easy to define. This is just norm of x is equal to 1. So this is nice. You can come up with polynomials that can capture this. So you can have all these nice sort of PSD constraints. But if you look at sort of more complicated things like a rectangle, so say my norm of x is less than 1 and my norm of y is less than 1, if I wanted to look at this boundary, I actually have an or condition. So I have that x is less than 1 and y is less than 1, or the norms of them are. It's not easy to come up with a polynomial that can capture that. So one of the nice things that we were working on is coming up with the conditions on the safe set in which we can define both the safe set and its boundary condition as polynomials. And basically what this allows us to do is look at the boundary as this product of our polynomials under some mild conditions. So again, this is nice because we can take these constraints that are normally positive semi-definite constraints and turn them to equality constraints. Okay, so this is nice because it basically makes the optimization easier. It allows us to capture more typical safe sets that we would see in robotics settings. Okay, so we have some relatively toy examples here. The toy robot example is this relatively simple system here. But again, this is capturing some safe sets. That typical work really sort of can't come up with good representations for. So even though it's relatively simple, this is sort of something that, again, from the theory perspective, is not sort of easy to do. Okay, so in short here, we're looking at sort of how we can characterize systems with sort of an additional layer of analysis. So this is sort of meant to augment, not replace, a lot of the more sort of formal or Boolean approaches to safety, but really sort of look at this in terms of the distributions of time, which again should give us a little bit more insight to the overall behaviors. Again, most of what we've been doing is sort of trying to improve the computation of this, so we can sort of reduce a lot of the difficult constraints and make things more feasible. So we're working on extending to states. Currently, we have some initial results where we're working on things up to about 6 to 8 state dimensions, but that's where a lot of the computational complexity comes in, as is usual. And again, we think there's some nice, sort of nice connections to perceived safety. So we're looking at actually doing some sort of user studies and design things, trying to connect these sort of abstract measures to something that's sort of more intuitive. Okay, so we have one more thing. I don't want to go over time since we started late, so I'll just sort of show some videos here. So we'll kind of go fast through this. But one of the things that we've been working on is these field robots. And in these sorts of situations, so this is sort of a nice clean situation, but sort of characterizing the failures in these cases So it kind of looks a little dinky, but it's actually hard to characterize these sorts of situations just because of all the complexities in the environment. But one of the things we did was try to codify some sort of different scenarios. So here's a view of normal behavior or sort of good conditions. As you can see, it's pretty messy still. And even though you can kind of see where things are, it does become tricky to actually just sort of figure out how to go up and down a row. We defined a few different types of collisions. The most common one, or the simplest one in many ways, is this row collision, where you basically just veer your heading angle a little incorrectly and you sort of get into a collision here. But then there are also situations where you have some obstacle that you actually can't traverse. In this example, it is hard to see, but that's sort of intentional. You'll get widely different sort of visibility conditions for these robots here. But this is actually where there's a stalk that grew in the middle of the road, so it just can't get through it no matter what you do. Another case that we sort of outlined is a traversable obstacle. So you actually see there's a plant that's basically just fell over here. So if you sort of applied a ton of torque, you would be able to get over it, but nominally you can't. So to look at these, we've been looking at anomaly detection. Since we have a hard time really characterizing the failures in these situations, anomaly detection sort of gives you this nice proxy where you might not be detecting failures per se, but you're detecting things that are sort of out of distribution or you have high uncertainty about. And it kind of helps address many issues like the fact that you don't have good data representation and whatnot. So we looked at a supervised VAE approach. We'll kind of quickly go through the details here, but basically this is a multitask approach where you're both looking at how to sort of generate or regenerate the situations that you're seeing, but we also sort of try to capture these class labels given what we have before from our small labeled data set here. What's nice is you get some interpretability from the data set. I won't claim that you always do, but in our case we kind of did, and you get good classification as well as anomaly detection here. So it's something that can work online. Another thing is it can work for very anomalous situations. So let's look at I think it'll go fast enough. So situations it's really never seen before, like a wild grad student, it can still sort of detect this. And one of the things that we've been playing around with is basically doing sort of more active inference for if you do misdetect or misclassify what type of failure it is. Okay, I'll do one more video and then I'll call it a day. One other sort of issue with this is it's very reactive. So this is a situation of a very bad failure. It's basically like this. So this is something that you don't really want to detect it when you're in this state. You never want to get in this state. So what you actually want to do is look at proactive or predictive detection. So we've been playing around with basically how to evaluate these systems here. And let's look at this one since it's pretty gnarly. This is the method that we're approaching. We take into account the future control actions here. So you can get basically a more predictive assessment of basically whether or not you'll hit an anomaly or, in our case, hit a failure here. Okay. Hopefully, at the end of the day, a lot of this detection in this sort of scenario will help us move to the point where we can actually really think about how we can remove the human from having to sort of babysit the robot very carefully. So it can move to these cases where we have one-to-many supervision, or hopefully eventually the case where we just have supervised control from afar. All right, so thanks for paying attention and sticking with me through that sort of whirlwind of discussion here. We talked about sort of many different approaches that you could take to trying to characterize or sort of understand failures and the sort of safety aspects of fairly different systems. And again, the key takeaway here is hopefully by understanding basically different ways to characterize these failures, we can have a better understanding of what will happen when we actually release them into the wild, and we're hopefully sort of actively working towards sort of improving everyday lives. So I'd like to thank all our sponsors and all the people that worked on this. And with that, I'd like to say thank you, and I'll take some questions.
Any questions?
I have two questions, one about the first half and one about the second half. So in the first half, you talked a lot about systems where you have models of the dynamics and you're assuming that you know those well. do you guys look at all, or do you have thoughts about how your uncertainty or how your analysis of like failures and things like that would be sensitive to model uncertainty, or is that too system dependent to comment on generally?
I see. So I think for the validation and simulation stuff, yeah. So you do need a good model, and actually the thing that it is most sensitive to is because we are looking at the most likely failures. It works best when you have a good model of what likely actions are. So you can sort of look at that sort of behavior. But if you're, say, trying to look at a pedestrian, there's tons of work trying to look into coming up with like a good model of those pedestrian behaviors. So having a perfect model there is fairly wishful thinking in many ways. So yes, you're right. So actually some of the work that we've been doing is looking at basically trying to come up with good proxies for that. So instead of looking or pulling from some perhaps incorrect probability distribution there, you can start looking at things like if it's sort of widely different from my last, it's probably very unlikely if you have some sort of Gaussian-ish behavior. So you can look for proxies there, but it is fairly sensitive to that, although you'll still find failures, but then the question is just, is it something that's relevant or not?
Yeah, that makes sense. And then for the corn example,
yes.
Were you directly just going from videos to predictions of failure, or like what were you predicting?
Good question. So the way we collected our data set was, so the way these systems sort of currently operate is they sort of have someone that's monitoring them the whole time. So you can actually get very quick labels on your data there. The problem is it's not a huge data set, so you do have to sort of make sure you have like efficient learning, and there's, you know, the nitty-gritty things for making things work there. But for that, so we were able to get the labels basically by these human supervisors since they're already doing these tests.
Cool. And then at test time, you're looking at videos and you're predicting directly whether a failure has occurred.
Yeah,
okay.
yeah. Although we also have it run online, but again, it's running it on the data and running it online. I guess it gives a perceived difference, but I guess from the analysis point of view, it's the same. So yeah.
Thank you.
Mm-hmm.
So thanks. So I'm curious about how, like, you seem to have, like, in the first chunk, you're talking about doing the safety and failure analysis for very complicated systems, maybe like perception and planning in the loop. Mm-hmm. And then in the second half, it's much more fundamental, like
yes,
as a stochastic dynamical system doing set-based analysis. How do you see those kind of complementing each other, or like pulling closer to like get more rigorous analysis of complex systems, or more, yeah, and kind of in that direction?
Yeah, this is a good question. So I think, I think this is sort of a very a big debate, I guess. So the trade-off is if you can come up with these like good sort of general models and these general approaches, you can actually get some guarantees, which is really good if you have like a specific thing that you want to check. So if you're trying to check some low-level controller or something like that, then you really want to have some sort of guarantees. But I think the reality is when you are looking at the complete system, where you are looking at these really complex perception systems and everything else, unless you put a lot of effort into coming up with like abstractions of those, you're going to have a really hard time actually applying these. So I would say these are sort of complementary. So for parts that you can, in general, if you can have some formal or very rigorous analysis, like that's what you want. You want guarantees. We want to make sure that we're meeting our criteria. But this is something that sort of is a much broader view, but we have basically no guarantees on coverage. You can get some sort of light guarantees, but they're similar to like the guarantees that you get with any Monte Carlo approach, which is sample a lot and you'll find it. So it doesn't really give you some good insight. So it's sort of, I think the one sort of open thing is, can you find something that can like inform the other? So for example, if you have some idea of basically maybe situations that are causing you a lot of problems, can you then more look at the formal approaches to sort of help fix it more rigorously? So maybe that would be I think the connection, but I guess that was sort of a non-answer, but hopefully it helps.
No, that's really interesting. Thank you.
Great.
Yeah, I think just following up on that last point, I was going to ask about like So if you can identify failures and categorize failures, it seems really useful. The next step is how do you fix them? I don't know if you want to say a little bit about how to connect that back to the original control design or something like that.
Yeah, this is a good question. So on some level, so the way that we've often been looking at it, especially for this case where we're looking at validation, often it's and I guess this is probably similar to what all of us do. You sort of see it, you try and debug it and find the cause, and then you'll kind of just hand fix it, which isn't very like formal or doesn't like give you some like good repair technique. There is some work in the formal methods community that tries to suggest, and I just use the word repair, ways to repair a policy and whatnot. But I think the more common approach is to actually take these sort of adversarial simulations and turn to things like adversarial learning or adversarial RL, where you're now not just trying to randomly sample or explore your environment at random, but you can look at these environments or these situations that are challenging. So you can basically try to optimize in this worst case as well. So adversarial RL does that, but it really, at the end of the day, I think how you actually fix it depends on your representation of your policy and basically the controller or whatever thing you're actually trying to fix. Yeah.
Any other questions? I think you kind of just answered the question that I was gonna make, which is the stress testing formulated as an active search problem or formulation, right? I mean, how is it? In which ways is similar to like active domain randomization techniques that people are using for I don't know, learning policies in simulation, for example?
Yeah. So that's actually sort of it is very similar. So often when you look at like domain randomization, I think the difference between this work and that is often, and there are some exceptions to this, but often when you do domain randomization, it's like you as the person training your policy are saying, okay, I'm trying to train my robot to navigate on the world. I don't want it to care about walls, so I'll just like randomly change all the walls or do the domain randomization, and these things basically I know I want it to not care about. So you're basically kind of enforcing what you want to not be important. So that's sort of the domain randomization view. This is more of thinking about how you can more generally produce these adversarial situations that push it towards failure, which is a different take, but they are sort of similar and whatnot.
Excellent. I don't know if there are any other questions. One more, we'll take it there.
So just observing like the agriculture case. So you are coming from an approach where it seems that you are not changing the speed versus you could like come from a different approach where you are kind of slow down significantly when you are in uncertainty. Which of the two you think would lead to better and faster convergence?
So in the agricultural case here, so this case, we are working with a sort of a fixed system. So we say, like, given the system that has its controller, which is trying to maintain a constant velocity. So it is trying to do that, and we're basically trying to assess and understand sort of failures that happen with it there. And then at this point, the only thing that we've really done to close the loop on this are either to sort of flag a human or try to basically go through a library of like pre-programmed recovery techniques. So if you found yourself in a road collision, you try to do a recovery and you try again, basically. So that's basically what we've done in terms of actually connecting it back to the planner. But this is a very good point where if we start having some uncertainty, especially in the predictive case, are there sort of very recovery-based or just stopping sorts of scenarios that we might want to do? So I think that's still something we haven't worked on, and I think in general that's a hard thing, since often most of the methods that you would sort of come up with to handle uncertainty do require some model or simulation. So I think coming up with sort of a principal way might be a little bit tricky. It's also, we haven't done much testing on how sensitive the perception is, or these failures are, to varying speed. But that's a really good thing to explore. So again, sort of a non-answer, but good things to think about.
All right. We're past time, so unless there are any other pressing questions, I think we're going to close it here. Thank you, Katherine.